Hi everyone, welcome back to this video series on Bitcoin. Turing Incompleteness. The Bitcoin transaction script language contains many operators but is deliberately limited in one important way. There are no loops or complex flow control capabilities other than conditional flow control. This ensures that the language is not Turing complete, meaning that scripts have limited complexity and predictable execution times. The script is not a general purpose language. These limitations ensure that the language cannot be used to create an infinite loop or form of logic bomb that could be embedded in a transaction in a way that causes a denial of service attack against the Bitcoin network. Remember, every transaction is validated by every full node on the Bitcoin network. A limited language prevents the transaction validation mechanism from being used as a vulnerability. Stateless verification. The Bitcoin transaction script language is stateless in that there is no state prior to execution of the script or state saved after the execution of the script. Therefore, all the information needed to execute a script is contained within the script. A script will predictably execute the same way on any system. If your system verifies a script, you can be sure that every other system in the Bitcoin network will also verify the script, meaning that a valid transaction is valid for everyone and everyone knows this. This predictability of outcomes is an essential benefit of the Bitcoin system. Script construction, lock plus unlock. Bitcoin's transaction validation engine relies on two types of scripts to validate transactions: a locking script and an unlocking script. A locking script is a spending condition placed on an output. It specifies the conditions that must be met to spend the output in the future. Historically, the locking script was called a script pub key because it usually contained a public key or Bitcoin address public key hash. In this book, we refer to it as a locking script to acknowledge the much broader range of possibilities of this scripting technology. In most Bitcoin applications, we refer to as a locking script will appear in the source code as script pub key. You will also see the locking script referred to as a witness script, or more generally as a cryptographic puzzle. These terms all mean the same thing at different levels of abstraction. An unlocking script is a script that solves or satisfies the conditions placed on an output by a locking script and allows the output to be sent. Unlocking scripts are part of every transaction input. Most of the time they contain a digital signature produced by part of the user's wallet from his or her private key. Historically, the unlocking script was called script sig because it usually contained a digital signature. In most Bitcoin applications, the source code refers to the unlocking script as script sig. You will also see the unlocking script referred to as a witness. See Appendix D in this book, as we refer to it as an unlocking script to acknowledge the much broader range of locking script requirements. Because not all locking scripts must contain signatures, every Bitcoin validation node will validate transactions by executing the locking and unlocking scripts together. Each input contains an unlocking script and refers to a previously existing UTXO. The validation software will copy the unlocking script, retrieve the UTXO referenced by the input, and copy the locking script from that UTXO. The unlocking and locking script are then executed in sequence. The input is valid if the unlocking script satisfies the locking script conditions. All the inputs are validated independently as part of the overall validation of the transaction. Note that the UTXO is permanently recorded in the blockchain and therefore is invariable and is unaffected by failed attempts to spend it by reference in a new transaction. Only a valid transaction that correctly satisfies the conditions of the output results in the output being considered as spent and removed from the set of transaction outputs UTXO set. Figure 6.3 is an example of the unlocking and locking scripts for the most common type of Bitcoin transaction, a payment to a public key hash, showing the combined script resulting from the concatenation of the unlocking and locking scripts prior to script validation. The script execution stack. The Bitcoin's scripting language is called a stack-based language because it uses a data structure called a stack. A stack is a very simple data structure that can be visualized as a stack of cards. A stack allows two operations, push and pop. Push adds an item on top of a stack. Pop removes the top item from the stack. Operations on a stack can only act on the topmost item on the stack. A stack data structure is also called last in, first out, or LIFOQ. The scripting language executes the script by processing each item from left to right. Number data constants are pushed onto the stack. Operators push or pop one or more parameters from the stack, act on them, and might push as a result onto the stack. For example, OPADD will pop two items from the stack, add them, and push the resulting sum onto the stack. Conditional operators evaluate a condition, producing a Boolean result of true or false. For example, OP equal pops two items from the stack and pushes true. True is represented by the number 1 if they are equal, or false represented by 0 if they are not equal. Bitcoin transaction scripts usually contain a conditional operator so that they can produce a true result that signifies a valid transaction, a simple script. Now let's apply what we've learned about scripts and stacks for some examples. In figure 6.4, the script 23OPADD5 or equal demonstrates an arithmetic addition operator OPADD adding two numbers and pushing the result on the stack, followed by the conditional operator OP equal, which checks that the resulting sum is equal to 5. For brevity, the OP prefix is omitted in the step-by-step example. For more details on the available script operators and functions, see Appendix B. Although most locking scripts refer to a public key hash, essentially a Bitcoin address, thereby requiring proof of ownership to spend the funds. The script does not have to be that complex. Any combination of locking and unlocking scripts that results in a true valid is valid. The simple arithmetic we used as an example for the scripting language is also a valid locking script that can be used to lock a transaction output. Use as part of the arithmetic example script as the locking script 3 op ad add 5 op equal, which can be satisfied by a transaction containing an input with the unlocking script 2. The validation software combines the locking and unlocking scripts, and the resulting script is 23 op add 5 op equal. As we saw in the step-by-step example in figure 6.4, when this script is executed, the result is op true, making the transaction valid. Not only is this a valid transaction output locking script, but the resulting UTXO could be spent by anyone with the arithmetic skills to know that the number 2 satisfies the script. So here's just the script here. The following is a slightly more complex script which calculates 2 plus 7 minus 3 plus 1. Notice that when the script contains several operators in a row, the stack allows the results of one operator to be acted upon by the next operator. 27 op add 3 op sub 1 op add 7 op equal. So I'm going to here today for this video. If you like listening, please consider like, sharing, subscribing, and give me a thumbs up. Thank you.